So let's have our next speaker come up, Mike Misener. So what you're going to hear from now is a real manufacturer making this stuff work. Mike Misener is Director of Injection Mold Tooling and Additive Manufacturing with Baker Aerospace Tooling and Machining. He's going to talk about these processes used in conjunction, conventional manufacturing such as machining, along with additive manufacturing, how they work together in real scenarios, how they make one another better. So, Mike Misener.
Good morning, everyone. Yeah, I come from the manufacturing world, so a lot of people look at additive manufacturing as taking over the traditional manufacturing world, and that's not necessarily true. It's going to enhance each other. And one of the things I want to talk about is how we've taken the All right, from the evolution of traditional and additive manufacturing to post-finishing of the additive parts, evolution of mold making with additive inserts, and some practical applications that are still in play. So combining complex geometries, we've taken traditional 3-axis machining, and we've made this particular part that you see in the picture in 4 pieces traditionally. It takes a lot of time, a lot of accuracy, a lot of checking, validating. So it's really taking a part of that nature and looking at it for additive manufacturing to be able to create that part more accurately, more quickly, and make it a better application for a fixture that I'm going to show you in the next couple of slides. So we 3D printed this in one piece. We're actually able to grow 2 parts at one time and grow those parts in the same time that it took to machine those. Now, in this particular application, yeah, we eliminated the machining, but we increased accuracy and timing with our customer. And then on the plastic side, we also have the same type of fixtures that we've got hybrid fixtures that we've taken the additive metals pieces in the plastic additive from FDM. We reduce the weight, we reduce the time, we improve the quality, and we've made it significant for our customers to come to us and say, you know, I need this fixture quick, everybody needs it quick. And how can I get this so that it's more user-friendly on the floor and reduce costs for them in the long run? Reduce costs for them up front, but there's more than just the original cost savings. There's cost savings once it hits the shop floor. And with those cost savings, you see there's a headliner fixture here. The center piece comes on and off. Traditionally, that was a metal piece that was traditionally cut, very heavy. A lot of times they took secondary equipment to be able to lift this off. Now they can reduce that down to maybe 1 or 2 manpower instead of 4, or adding secondary equipment to be able to lift this off the fixture, put it back on, and be able to use this on the production floor. It's very durable. We did some studies on the durability of these parts. We've had these parts, some of these in process for 2 or 3 years. Did some draw tests, did some durability, did some validation. The parts are very stable, long-lasting parts, and it's very user-friendly. So if you do drop this on the foot, it's not going to crush your toes. It's not going to damage the part, and it's been a very successful in the automotive industry. I know a lot of people talk about aerospace, a lot of the other markets. But we've really been working closely with the automotive industry to help enhance and reduce cost and reduce timing for their fixtures, because, like I said, everything is fast today. So we've taken some 5-axis post-machining, and the way we look at this is we are a manufacturer and machining company. So when we started looking at additive manufacturing, we looked at how we can take that part and use the software, but at the same time use our knowledge and ability and experience to be able to take these parts, set these up, grow these parts so that they can be finished in an efficient way, which I think a lot of people still need the education and the understanding of how to be able to grow these parts, be able to machine these parts in post-finishing and be accurate and efficient with it. A lot of us today think it's still a magical world. We take that software, we grow the part, we cut it off the plate, we clean the supports off, now we have to post-finish. And a lot of people have the hard understanding of how do I set this up and how do I post-finish it now that I've got it off the plate. Where we've taken the approach of taking the traditional side, we brought our team together, we look at the part before it even gets designed, figure out the best design, the best setup for the software to be able to grow the part, how we can stage that and set it up, and in most cases we can take these parts, finish them right on the plate, and as we do our final cuts, the parts come off the plate complete. That's a huge benefit, and it's a huge problem for a lot of companies out there that don't have the machining background. And the additive manufacturing is great, but if you can't finish it afterwards, it doesn't increase the efficiencies of what the actual purpose of the part's going to be. So the best thing you can do, again, is educate. We're going to talk about it a lot today. I'm sure the other speakers are going to talk about it as well, is we need to keep educating our people on the best cases. The previous speaker mentioned about the software. The software is improving. It's not quite there yet. We have a lot of work to do, but at the same time, we have to take our traditional minds, open them up and be able to think outside of the box, but at the same time, look at these and figure out how to utilize that software. Like I said, I'm a tool maker by trade. I look at these projects and say, okay, how would I traditionally machine this and how would I traditionally build this? And then take that experience, bring it into the additive world, figure out how we can design that and put the best possible case together for growing the part accurately, making the post-finishing accurate. There's a lot of heat treating, hipping, those kinds of things that go on, so all that's going to be taken into account. So the biggest thing is education, lessons learned, best practices, and you can take an additive part and finish it, post-finish it on machines complete without losing any kind of time or accuracy. Just another example of how we optimized the design. We looked at this part, we figured out how we could machine it. We designed it to the fact to be able to get what the customer needs. We redesigned some things in there, figured out how we were going to be able to machine it, and then figure out how we were going to grow it so that we understood the best practices afterwards. We're giving the customer the best part possible. Everything fits within their criteria and their needs. And then we grow the part, we validate that, we make sure that everything is validated. We actually use laser trackers and other means to be able to validate everything right out of the machine before it even goes to the next step. We can do all of our post-processing again on the plates, finish these machines and cut these off so that we've got every angle covered. A lot of people talk about conformal cooling and everybody thinks about high pressure injection molding, and that's great and that's been a huge benefit, and I know that's where conformal cooling originally started. Conformal cooling is a necessary part of injection mold. Of course, it reduces cycle time tremendously if it's applied correctly, and a lot of that has to do with the design, but To take it even further, we look at it as uniform thermal surface control because you're looking at your tool to be uniform temperatures throughout depending on the mass and the different areas of the part. So we look at this as not only cooling, but on the compression mold side, we've also applied it to compression molding for heat distribution. A lot of compression molding, you've got to maintain heat on a heated tool to make sure it doesn't cool off in between cycles. When you put the part in, it draws the heat out. It works very similar to conformal cooling, but typically in the heated tools, you have to be able to control those local areas of temperature individually. So sometimes it needs to be enhanced just a little bit to be able to maintain that temperature throughout the tool. So that's a big part of conformal cooling or uniform thermal surface control is to be able to maintain it, control it, reduce the cycle times. It makes a better product, it improves quality, and gives the operator a much larger window of process to be able to control the part and get a better part at the end of the day. Reduces warp, reduces sink, of course the cycle time, and it's very important to be able to optimize the heating and cooling in the tools. This is an example of conformal heating. Again, you got a real deep rib. You've got a BMC material. So you've got the same kind of problems to where that area in there, you can't get heating in there, so it cools off rather quickly and it needs to be maintained. So there's a deep rib structure here that typically you can't get the heating into. You can't keep it all the way up at the tip. There's about a 5-inch drop inside of those ribs. So when molding that traditionally, you've got a long cycle time, you pull that out, you still have some rib detail that's not completely cured as it should be. So by putting the heating in there, we're also getting a better structural part. It's maintaining that the part gets the even heating and keeps that part a lot stronger in the areas that it needs to be. And again, enhances the part in the surface quality. Surface quality is a big case where it transfers heat from the backside to the core side or cavity side, and it gives you a lot better looking part, reduces the warp and sink again, reduces cycle time, and that's on compression molding. That's been a huge benefit to our compression molding companies that we're dealing with. And again, we take these inserts, we look at these without changing the actual data of the part. We bring our team together, we look at how we can grow these inserts in the additive manufacturing, get the internal channels, and be able to post-finish these the same way with accuracy and be able to put these into the pockets of the tools without causing any kind of problems with fitting or making all the details 100% correct. So we've also been working with some of the companies on the injection mold side that some new technologies out there or some advanced technologies out there for injection molding. A lot of it's not really new. It's been out there for a while. It's been struggling to break into the world and say, this process is going to make a better part. So we've been working with some companies for rapid heat, rapid cool. We've been able to put those inserts in and be able to control each one of those in particular circuits and be able to maintain the cooling or the heating that needs to be done, which has really enhanced the process of rapid heat, rapid cool. Some of the minor imperfections that still result from rapid heat, rapid cool have been eliminated. We're getting a lot better, cleaner part. Your Class A surface Those are non-painted parts, so that's been a huge benefit, of course, to the automotive world, to be able to reduce paint lines or eliminate paint lines and be able to go from a painted part to a shoot and ship part and reduce cost of the part considerably. We've also been working with mule cell. From truck cell, we do the low pressure molding with that, and with the additive in there, that also has helped the flow of the material, where we can actually heat and cool the tool variable in different areas to be able to enhance their process and make it more even and get an even flow of material, which has also reduced cycle time and improved part and improve the integrity and structural integrity of the part. So yeah, basically we start out, and the first thing, everybody looks at is, oh, it can't be done. We always say, yes, it can. We figure out how to get it done. We bring the team together with our engineers. We look at what is the best possible scenario to develop the part at hand, and we work together as a team to bring it all together from beginning to finish. And it's all done up front before it actually hits the shop floor. So we take our knowledge and our experience from being able to do this, and like I said, our best practices, what our experiences are, and use these as proven applications to be able to create these parts accurately right out of the gate. So we have to think outside of the box. You got to be creative with how you're going to manufacture this, not only how you're going to build it, but how you're going to manufacture it. So we look at it as, if you can think it, you can bring it to reality. So there's a lot of things that people look at, and getting them outside of the box has been difficult. As many of you know, a lot of people are still resistant to the fact that, is it strong enough? Is it durable enough? Does it have the longevity that it's going to use in the traditional methods? Are the materials going to change? Are we going to add materials? Are things going to get better? And like even the previous speaker mentioned, there's a lot of things still in the infancy that's growing, but I think we've proven the fact that this technology is definitely key for the future. It's going to help us all get better. It's going to reduce costs. It's going to reduce time and make everybody more profitable and really be a lot of fun. I mean, being into the additive world, like I said, I came from traditional background. Getting into the additive world has been challenging, but at the same time it's been fun because you can think outside of the box. You can make things happen that you never thought could happen before, and be able to take the traditional minds and turn them into the additive minds on how we start this project from something that looks really scary into something that's pretty simple, and we can complete and make accurately, on time, and make our customers happy. So there's a lot of things that we have to do yet in the additive world to make the parts better. He talked about failure rates; those kinds of things happen. But again, you take your lessons learned, you can apply those to your traditional thoughts. You can put your best practices together, and when you manufacture any part, you need to really think about it, understand the process, design for the process, because you can do unique designs and that'll make the part actually stronger than a solid part and make it a lot more accurate to manufacture and a lot more accurate for the customer in the end game.
Got some time for questions as well. On the previous slide, he said, what were your words? Start with yes and figure out how. So how much faster would innovation proceed in all of our different walks if that was the philosophy? That's actually, that's a tweet right there, if you're active on Twitter. Hashtag for Twitter to engage with this conference, IMTS Additive, all one word, IMTS Additive. Yeah, let's all tweet that. Advance that idea. Any questions? Hold up your hand high if you do. What I liked about Mike's presentation, if you're an enthusiast in discrete part manufacturing like I am, you're basically a workpiece nerd. So there's a lot of rich material in that.
As an aerospace parts producer, what types of issues have you seen with certifying the materials before you produce the part and after the part has been completed?
Give that to me one more time.
Yeah, as I assume some of these are aerospace parts or not, what types of issues have you seen in certifying the actual material that's used to produce the part before and after the part production?
Basically, we've looked at it, and one of the major problems for the different materials and the different manufacturing of equipment actually is the porosity that you run into once in a while with internal channels that you have to look at. The hipping process can take care of a lot of those issues, but there's still a little bit of tweaking that needs to be done to the machines for the internal channels so that you don't have the porosity and cracking, that kind of stuff that can develop in the part. And a lot of that, again, is lessons learned on when you need to tweak the parameters, when you need to do some post-processing, some stress relieving, that kind of thing, at what stages it needs to be done. So once you understand that, you document it. We've been very successful at moving forward and eliminating those issues, but those are things that you learn as you grow the parts.
Other questions? She sees one.
Bill Mineralytics back here. Thank you very much for the presentation. A question for you as you transition from R&D and prototyping and production in terms of being a service bureau. Can you address some of the key challenges, please? And thank you.
That one also. Give that Bill one more time. We both, neither one of us quite got it.
Okay. In terms of being a service bureau and the transition between prototyping and moving more towards production parts, could you talk about the challenges of a firm your size making that transition?
From prototype to production, of course, one of the challenges for the additive world is being able to produce enough parts, because it's rapid prototyping, as everybody thinks. It's fast, but it's not as fast as traditionally making a part, for sure, a traditional style part. But what we've been able to do is take those prototype parts, figure out how to post-process those, and take those from beginning to end, and be able to reduce the time from traditional machining to additive manufacturing, and get into volumes. You're not getting into high volume yet in this industry with metals printing anyway, but it is coming. It's getting better. It's getting faster. Are we ever going to be able to produce 1 million parts without a lot of machines? Probably not, but I think there's going to be a lot of enhancements in the future that's going to help production fall into this additive manufacturing.
Do we see any others?
Yes, over here.
Okay.
In the beginning of your presentation, you mentioned that the software isn't there yet. What do you need the software to do that it's not doing right now?
Well, it's like everything else. I mean, the software is very good. It's very helpful, but you still have to take common sense and look at the software and how you set the parts up, how things are manufactured. The software is is very good, but it needs to get a lot better. Failure rate a lot of times is due to support structures, those kinds of things. The software will generate automatic supports, but typically those automated supports aren't good enough to be able to be a successful build. So you have to take those, take your knowledge and your experience and be able to take those supports and turn those into something that's going to be successful on the build throughout.
We could do one more if there's, I do see a hand here.
Like the gentleman was asking earlier, for the aerospace components, are you able to supply the customer with a certification for the metal?
Supply them with what?
Are you able to supply for the aerospace industry? Are you able to supply the customer a certification for the metal when you deliver the part?
Yes.
You are?
Yes.
And as far as porosity is concerned, do you have to x-ray the part to make sure that even though the metal is certified, that porosity, which could be a structural issue, how do you make sure that that part does not have porosity in it? How do you guarantee that to the customer?
For the most part, it's done with x-rays, MRIs, those kinds of things, or CAD scans to be able to validate throughout the part. There's still a certain amount of parts that have to be destructive testing to make sure what's inside. There's penetrative testing, so there's a lot of testing that can be done, but x-ray is the most accurate, and it's going to be able to validate a lot of the parts without destructing and destroying the part.
I think we'll call it there. I don't want to be prejudiced against people in the back that I can't quite see because of the lights. I think we're good there. Mike, thank you. Mike Misener with Baker Industries. Thanks so much.